That way I don't have to edit them. Okay. Group B, we're going to talk about digital stuff. So there's one question out of this group. Digital circuits operate in two binary states. We represent it as a 0 or 1, a high or a low, on or off, 1 or 0. You'll see some stuff later where we call it mark and space, anything that represents the two different states. And we represent binary numbers as a base 2, so it's 2 to a power. So 2 to the 0 power is going to be equal to 1. 2 to the first power is going to be equal to 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. And turns out that those power numbers will be how many bits there are to represent that number. A little chart over here, I'm showing the conversion from a decimal value to its binary and what we call a binary coded decimal, how you represent a decimal number with binary, and it takes 4 bits. So 0 is obviously all zeros, 1 is 1, 2 is 0010. Okay, so we just count up until we get up to 7, which is the 8th number. Then it has to roll over to the most significant digit. So 8 is going to be 1 plus 0, and 9 was, we just add one more to it. Now this can go all the way up to 1111, which would be equivalent to 15. And that would be a hexadecimal representation. They don't ask you about hexadecimal on the test yet. Okay, a typical logic circuit, one of the basic ones is an AND gate. It has, in this case, 2 inputs. It can have more than 2. You can have 3, 4, possibly more. This is called a truth table, where you represent all the possible values. So the 2 inputs can be either 0 or 1. So there's 4 states. So they can both be 0, they can both be 1, or one can be a 0, one can be a 1. In the case of an AND gate, which says A and B, for the output to be true or 1 or high, whatever you want to call it, both of the inputs have to be true. Now, there's also what's called a NAND circuit, which is an AND gate. You see the little inverter signal, and it just inverts the output. So whatever it would be as an AND, this is going to be the inversion of it. So in the case of anything other than 1 and 1 on the input, the output is going to be true. It will only be false when both inputs are true. So it's just the inverse of this truth table for the AND gate. And we normally, when we write these in Boolean algebra, we use this overscore sign to represent that it's the inversion of A and B. Next, we have an OR gate, which is what it says. It's the output of A or B gives you Q. So in this case, if either A or B or both are true, its output is true. So the only time it's giving you false is when both of the inputs are false. Likewise, we have a not version of the OR, which the NOR we call it a not OR, and the NAND was a not AND, and this little circle we call a NOT. In this case, its output is only true when both inputs are false. In any other case, its output is going to be false. So, which of the following describes the function of, okay, I guess I can't get rid of that, of a two-input AND gate? Remember, it's an AND, A and B. Yeah. Okay. Only when both inputs are high. Now, if that was a NAND gate and both inputs were high, what would the output be? In other words, a not AND.
Be low.
All right. Okay, digital integrated circuits. They usually have a lot of gates and flip-flops, counter, shift registers, things in them, depending on what the function is. A flip-flop is basically a circuit usually made out of two or more gates that has two stable states. In other words, it can basically store a 1 state or a 0 state, true or false. A binary counter is an array of usually flip-flops that's set up so that it counts pulses, counts up in binary. So every time it gets an input clock signal, it will increment in binary all the way up to the number of stages in the counter. So if we had a 3-stage counter, that could count up to 8, 0 through 7, 8 states. A shift register is another array of flip-flops such that when there's an input, every time it shifts that 1 or 0 on the input to the next stage. So it basically shifts the value of that input through the shift register. So if you had an 8-stage shift register, it would take, and you start off with a 1 on the input, every clock, it's going to move that 1 to each stage until it falls out the end. And normally you could do something with that, like start it over or use it as some sort of overflow. The key thing is it's a clocked array of circuits that passes data in steps. Okay, here's a typical 3-bit binary counter made with 3 what we call JK flip-flops. And there are several varieties of flip-flops that behave a little bit differently. In this case, here's the waveforms, the output of these 3 stages. And every time there's a clock, you can see it's going to count, and Q0 being the least significant bit, it's going to count up 1, 2, 3, 4, 5, all the way up to 7, which is the 8th state, because we start at 0. and then it starts over. So a 3-bit counter can count up to binary 7.
Things that didn't start at 0 and go to 7, say, 0 again.
Well, this is the 8th clock pulse, so it's going to roll over to 0.
It's covered by the.
It can only hold 8 states,
Yeah.
2 to the 3rd.
It's covered by.
Oh. Yeah, that thing's always in the way. I don't know how to make it go away. Yeah. So there, to represent 8 in binary requires 4 bits.
Yeah.
It would be 1 0 0 0.
Yep.
And it's a 3-bit counter. So when you get the 8th clock pulse, it's going to roll over to 0.
Things aren't lined up quite properly on the numbers.
Well, that's possible. Yes, the 8 should be over here. I'm glad you pointed that out. I'll fix that.
Yeah, should have zeros on both ends.
Right. Okay. We have a digital shift register. This one has 4 stages, and whatever is on this input, when we get a clock signal, is going to get shifted to the next stage. And the next clock, it go to the next stage. This is kind of what the waveforms look like. At the bottom, we have our clock signal going up and down. And with that 1 on the input on the first clock, it's going to change the output of that first stage to a 1 until the next clock. It's going to go back to a 0, and the next stage is going to go to a 1. The next clock, it moves to the next stage, so on and so forth, depending on how long the shift register is. So how many states does a 3-bit binary counter have?
Yep, Kookaburra.
All right. What is a shift register?
Alpha, Allegro.
All right. Okay. Oscillators. A sine wave oscillator, and they don't have to be sine waves, but in this case, we'll keep it simpler. We need an amplifier, a feedback circuit, and a filter or tank circuit to determine the frequency. So the way it works is you have, in this case, we're going to have an LC network that is resonant at some frequency. So in order to keep that resonating, we have to keep supplying power to it, and we do that by using an amplifier that's connected to the tank circuit and taking part of the output of that amplifier and feeding it back in phase or positive back into the resonant circuit. And the key thing, it turns out, is the feedback from the amplifier has to have an overall gain of 1 in order for it to sustain oscillation. Now, it may take a gain of higher than 1 to get it started, but in order for it to continue oscillating, the feedback has to be just enough to offset the losses. So the gain is 1 around the loop. You can also construct them without an LC network where you'd have, say, an RC filter or something that would also only pass the frequency that you want it to operate at. It's easier to do it with a LC network or what they call a tank circuit from the old tube days. And I think they called it a tank circuit because you're storing energy in the inductor and the capacitor, and this is going back and forth from the capacitor to the inductor and at its resonant point. So as long as you're making up for the loss in energy from the transfer, it will oscillate forever. Which of the following are basic components of a sine wave oscillator?
Delta.
What determines the frequency of an LC oscillator?
Open barrel. Sure.
They gave you a clue here, the LC oscillator. Okay, amplifiers. There's several characteristics of amplifiers. One is efficiency. So it's defined as taking the RF output power and dividing it by the DC input power. So if I had an amplifier that output 100 watts RF, RMS, and it takes 200 watts of DC input, then its efficiency would be 50%. And that's not atypical. It's good for any transmitter.
And all the rest of it is heat in the radio
Yeah.
shack.
Yeah. Okay. Another thing is linearity. Okay. And that's how well the output preserves the input waveform. So in most cases, like audio in particular, but for RF stuff, you want the amplified output waveform to be an exact copy of the input, only more power, higher voltage. The other thing, it's mostly from the tube days, but it's still a possibility with transistor power amplifiers, is neutralization. So remember, for an oscillator, it's an amplifier with feedback. Okay. So if I've got an amplifier, there's always the possibility of some feedback due to stray capacitance and the magnetic field interacting with the other parts. So you could actually get oscillation at certain levels. So neutralization is adding some circuitry to compensate for any of that feedback that you don't want, so it doesn't turn into an oscillator. The chart is showing different classes. The class A amplifier, which is probably the simplest. It has the best linearity. The output will look like the input, very little distortion. The downside is it's very inefficient because the output transistors or tubes, in the tube case, are on all the time, so there's a lot of loss. They came up with the class B, and they operate those normally in a push-pull fashion, so it requires two transistors or tubes, and they amplify half cycles like the full wave rectifier. You have what's called crossover distortion, where you go from one half cycle to the other half cycle, they don't quite match up, so you get some distortion at that point. They came up with a modification called a class AB, where they actually have some overlap between the half cycles to try to compensate for that, but it's a little less efficient than a Class B. And then you've got a Class C, which is the most efficient of these linear ones. And it actually amplifies pulses and requires a tuned circuit. So you're almost like an oscillator in that you're keeping that output circuit resonating. And the other classes up here, D through T, and I don't know what a T is, but those are digital amplifiers, and they work a lot like the switching power supply, okay, where they will convert this, they will sample the signal into a pulse width modulated signal, and then it's easy to amplify that. It's just square waves, and it's either off or on, so you have very little power loss. And then you filter it back and make a sine wave out of it at the end. And down here, we're showing the conduction angles where for Class A, it's on 360 degrees. The Class B is 180. And you get down to very, very low conduction angles for the digital amplifiers. So for Class A, it shows a typical circuit. Your operating point is normally over here in the middle of the linear region. So you're going to amplify that signal, both waveforms of it. So it will be actually at a DC offset. The key thing is it's low efficiency, about 20-25%. Very low distortion. It's on 100% of the time, and it preserves the input waveform. For Class B, we get up around 60%, but you've got some crossover distortion because of the two stages, because you're amplifying the positive and negative peaks of the sine wave independently. The Class AB is a modification, and they do some things with the biasing so that it's on for a longer period of time, and tries to compensate for that crossover distortion. But because of that, it's a little less efficient. Class C is the most efficient of that series, up around 70%. It has the most distortion. It's typically used if you're doing CW or FM because they aren't sensitive or shouldn't be sensitive to amplitude variations, just frequency. So the fact that this has some amplitude distortion doesn't affect CW or FM. But it does require some sort of resonant tank circuit in order to operate. So you're just amplifying pulses that you're feeding into this tank circuit to keep it resonating. And then the Class D, which I said you're going to take the input waveform, sample it, come out with this pulse width square wave, which you step up to much higher voltages or currents, and then filter it back to a sine wave. So there's, depending on how fast you sample it, what kind of filtering you have will determine how much distortion you get. I think they are doing high-end audio amplifiers that are Class D, but they're not cheap.
And they don't sound quite as good as an old Macintosh tube.
That's because tubes have distortion.
Harmonic distortion.
People like the color of the tube sound. Okay, in a Class A amplifier, what percentage of time does the amplifying device conduct for Class A?
Allegro.
Which of the following describes a linear amplifier?
Let's see. Bocachica?
Output preserves the input. Which of these classes of amplifiers has the highest efficiency?
Yeah.
Class D is higher, but it wasn't on the list. For which of the following modes is a Class C power supply appropriate for amplifying a modulated signal?
Follow, Boca.
Right. Because single sideband, which is basically AM, really care about amplitude distortion. FM doesn't. How is the efficiency of an RF amplifier determined?
No problem.
Remember we talked about the efficiency of a 100-watt transmitter amplifier?
Yeah, what he said.
Huh?
Yeah, what he said.
What he said. The output power by the input power. That's how you normally do efficiency for anything. Output divided by the input. What's the purpose of neutralizing an amplifier?
Boca. Yeah, well.
Right. You don't want it to be an oscillator. Okay.
Actually, in audio, your customers will not like.